Hello.
Bonjour.
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 Buongiorno.
Buongiorno.
Italian over French.
Salut. Vous m'entendez?
Oui, très bien.
Super.
So it's starting to record automatically.
I saw that.
So Cyril might not be able to join, so he wanted us to record.
Yeah.
Hi.
Hi.
Hello.
Okay.
Hi, Carlo.
What time is it, Carlo?
It's 5 o'clock in the morning. I'm
Oh my gosh.
If I say something stupid, just don't bother.
That's impressive. Thank you.
Thank you very much. Gives pressure.
Hello.
Hey.
So there are still 5 or 6 people, so I suggest we wait a bit.
Yeah. How long are you staying in Canada, Carlo?
Inshallah, it depends on the lockdown. I was blocked here by the plan was to come back to France more or less now, but my flight had been cancelled.
Okay.
So I'm waiting for, I think in principle, I might have the right to come back, but it's strongly not advised for the moment here to move, to travel. And there are very few flights. So I think another month probably I stay here. And then if the situation normalizes, I come back.
There is a lockdown ongoing in Canada these days.
That's correct, yes.
A strong one or
no,
a Chinese one?
No, it's sort of reopening. We are like Italy and France, but a bit late. So it's beginning to reopen now. And the international flights is very little, and most flights have been cancelled. But the recommendation is not to move, so I'm just following them.
Yeah.
France is open now?
It's reopening, I mean, and since the beginning of this week, we are allowed to visit bars, restaurants and stuff. So it's almost back to normal, apart from the fact that people are hanging around with masks now. And
I would say even too much. I mean, I saw some restaurants and bars near where I live, and I think people are underestimating the possibility of a second wave. I saw so many people in bars.
Yeah.
Yeah. We'll see. I mean, I think everybody expects a second wave, no?
Yeah, experts do. So.
Everyone, yeah. But right now, looking at the figures, there's nothing like that. It's been almost 1 month now that France is unlocked and nothing is really happening.
Yeah, I mean,
I guess in the past few days, they increased the number of cases in France, no?
Sorry?
In the past few days, I guess 3 days or something.
Increasing?
Increased the number of cases, not deaths, but
yeah.
It's expected, no?
Yeah.
But there might be 1 or 2 weeks delay between them.
Yeah, that's what I would expect. Beginning of July, I think we will know whether the reopening has some sensible effect.
God save Zoom. Well, at least the good point is that you have built a very nice reading group, Christian. It's really amazing. I mean, nothing like that would have happened without the lockdown. So
thank you. I exploited the lockdown in the best possible way, I think.
yeah, but that's great job. Thanks a lot.
I appreciate that.
I'm in touch with more people now than before this way.
Yeah,
exactly.
yeah.
And me too. I've been doing things that I wouldn't have done without the lockdown. Okay, I think not everyone is here, but I guess we can start.
Yeah.
Richard is here now, so now we are definitely. Laurie, maybe only Laurie is missing, but she will probably join. Okay, so yeah, as you know, this week and the next one, we will have Alexia, Auffeves, which you know very well, every one of you, and Philippe Grangier next week. They will talk about their work on foundations. I shared 4 papers with you. I hope you had time to have a look at them. So they will give presentations, and then we will have time to discuss. So Alexia, take the time you need. I don't know if you have slides or stuff to share.
I do.
And besides, we are recording the meeting, so I'm gonna kindly ask you this time to switch off your microphone so that there will be no noise in the recording. And I'll let you know what I will do with the recording. So thank you, Alexia.
Thank you. Okay, so the animator has deactivated the screen sharing by the participants. So I need some action from you, Christian.
That's not even something I knew I did. So, okay, let me.
You ignore your power.
Okay, let's try multiple. Can you do it now? Because I have 2 options.
Yes, I do.
Sorry about that.
You see my screen?
Yes.
Yes.
Fine. Okay, so yes, so we are going to present with Philippe our work on that was called System, Context and Modalities. This is a 2 voices talk. I'm talking this week, Philippe is talking next week, and the philosophical help that we had was provided by Néel Farouki, all along these past years. So it's a philosophical reading group, so this is the fuel that will feed the thoughts today. This paper here was published like 4 years ago now. This one was 2 years ago. It's in French, and this is the only paper where Philippe, Néel, and myself signed together. And this one is from last year, and it was following a meeting at the Royal Society where I had the opportunity to meet Carlo for the first time, and we start recognizing ourselves as cousins. So I'll come back to that point later. Right, so again, this is a 2 voices talk, and today what I'm going to present will be free from mathematical formalism. So this is going to be very difficult for most of you who practice quantum mechanics with the formalism all the time, but I would like you to try to make the exercise to forget everything that you know about the quantum formalism. This is gonna be about ontology. This is gonna be about phenomenology. Basically, the strategy that we are going to take is starting with phenomenology, experimental one, postulate an ontology, and then provide motivations for the theory and the formalism. And I'll stop at that point, And then next week, Philippe will focus on the quantum formalism itself. And so I anticipate a little bit that he will show that the best possible model for quantum ontology is provided by the quantum formalism that we know. And as you're going to see, today I'm going to talk a lot about the bipartite nature of reality, the fact that there are not only systems, but systems and context. And this bipartite nature of reality, it appears that it has a natural mathematical interpretation, so that will be presented again by Philippe next week. Okay, to finish the warm-up, this is the outline. It's very simple. The first part is devoted to our primitive ontology, and basically I'm going to talk about what Philippe dubbed a long time ago contextual objectivity. Then I will switch. I will show that this contextual objectivity is actually the cause of randomness. So randomness can be actually a consequence of the ontology and not something that comes in the package in the very first place. And this motivates the quantum formalism, and then I'll go to the conclusions. So that's for the program. Okay, and since we are talking about ontology and reality, I could not resist to present you a picture of Néel and to induce a questioning à la matrix. So I would like, okay, I asked you to forget about the formalism, and now I'm asking you to take a breath, look at what around you, and actually the best possible philosophical experiment that you can do is to look if somewhere you have a cupboard or a fridge or something when you can open and close the door. Do you have this? Can you do this? Can you take something and open the door and check what's inside? Okay, here I have a cupboard. I'm going to open. I see files. What makes me think that this file exists? Now I don't see them anymore. So to check that they exist, I'm going to reopen this. They're still there. And then I'm a bit paranoid. I'm going to reopen. Okay, they are still there. Right. So basically what makes me suppose that that thing exists, it's repetition. It's the fact that I can, as much as I want, check that this thing is here. I have the repetition under my disposal. So I can make the assumption that this thing exists. So then Néel answers, okay, but that thing exists, yes. It's because I can repeat my measurement. I can check as much as I want, it is here. That's the first test. The second test, well, the microphones are shut down, but I would otherwise ask you to open your microphone and check with me. It's intersubjectivity. This feeling that one thing exists, it becomes stronger if I can share this with other people, and we can agree all together that there are files in my cupboard. Okay, so two criteria: repetition and intersubjectivity. And then Néel is more and more convinced that thing exists, even if no one is watching, even if I'm not opening the cupboard, even if no one is here with me to check. So I can make the assumption that this thing is objective, it is real. And then Morpheus answered, but these are guesses, okay? These are guesses. And the ontology, it's always postulated. And here I'm going to say something which is a personal way of express ontology, because I'm not a philosopher, I'm just a physicist who likes philosophy. Ontology, for me, it appears to be the most efficient model to account for my perception and to account for my measurements, okay? All this long introduction to tell you that our job in this meeting that we have together will be to take some freedom on the ontology that we use. and to be aware of what makes us postulate that this is real and this should behave in this or that manner. Okay, right. So once we have this first consideration, I can go to basic ontology. So the basic ontology that we are going to take is based on a realist postulate. There is a natural world outside of us that exists independently of us. So we are not in the matrix, in other words. And this natural world, I will claim that it's made of systems. Systems are finite entities of the natural world. I can split the world, actually, in many different parts. And these systems, they are objective. They would exist even if no one were there to observe them. In addition of this, there are events. So here are different ways to express the same things, but in the rest of the talk, I will talk about events. But these are phenomena, these are state of affairs, stuff on which people that they can agree. So events, they are objective. They exist even if they are not observed. They are actual, meaning that they are realized, meaning that they would be the same for every potential observer if they were observed. And repeated events are the reason why we can postulate something about reality. Okay, just like here, I opened my cupboard many times, checked the file was there. These are repeated events. And that's why I could postulate that these files are there. Okay, and now something a little bit more original is that I'm going to say that around the systems, systems are basically not alone. Around the systems, there are contexts. So context, basically, it's something that is around the system. And this is very, this is very logical, right? We have a natural world that is pretty big. I cut a small piece of this world. If the piece is small, there is always some stuff remaining around it. That's what I'm going to call a context so far. So a context, this is something that is bigger than a system around it, but smaller than the world itself, okay? And contexts, they are made of the same stuff as systems. So I'm very general here. Okay, these were considerations from the everyday life. Now I'm going to orientate a little bit the debate and go to physics, okay? To start using words of physics. So the natural world in physics, it's becoming the physical world that we want to describe. The systems, they are the systems we want as physicists to study. And around the context, that will be the experimental context, that will be the measuring devices, okay? And the measuring devices, usually they are prepared in a way that they correspond to a question asked to the system. So here, the ultimate kind of answer we can extract from this kind of experiment, it's a yes or a no. And that's what I'm going to use later. The event is the measurement outcome, and it's an answer to the question, okay? So basically, the picture is the same, but the way to, the motivation of the thing is now oriented towards an experiment. So once that we have installed the basic ingredients, we can start asking another question very important in ontology, which is the notion of state. What is the state? Because with this, we can start building what we mean by state. So I'm going to take an operational approach here. One builds a state by asking a system a series of questions, and then we fill the ID card of the system. So for instance, here I have a table. My computer is sitting on a table. This table, I can see it's brown and it's made of wood. That's the ID card, and I'm ticking the ID card. So, and each question is asked within a given context. So this is what we do. Basically, I have my system. I have my first context here that corresponds to the first question. I get a yes. Then I take a second context. Then I get a no. Keep on filling the ID card. Third context, then I get a no. And all these answers here are, again, starting to fill the ID card of my system. And now, what's happening in the everyday life and in the classical phenomenology? In the classical phenomenology, what we observe is that I can obtain repeatedly the same questions to the same answers. If I ask my question 3, I get a no. If I go back to my question 2, I get a no, and etc. So I get a repeatability in the answer. So this brings me back to the first slide. This repeatability gives a feeling of certainty. So here we are in the psychological level, but from a physical level, we have a predictability with certainty, okay? And this allows to upgrade the ID card of my system, which is an operational concept, into a state, which is an ontological concept. So I'm going to explain, basically, the repeatable answers that I get by a permanent cause, which is the existence of a state. This is an unconscious path that we follow, but that is, well, that is present, actually, when we make this postulate that there is a state that exists. Okay, so the conclusion of this is that in the classical world, what we observe is that the state does not depend on the ordering of the questions. Like I said, I can go back to any question I asked previously and I will get the same answer as before. So basically what I can do is I can forget about the context and I can attribute the state to the system alone. And that's what we do. When I ask if my table is, what is the color of my table and what is the material of my table, I don't remember which context I use to ask this question. I just say, my table is brown and it's made of wood. So in the classical phenomenology, what I get is that my states, they are non-contextual. They don't pertain to the context anymore. They pertain to the system alone, okay? But this intuition that states pertain to system alone, it is built in the classical world. And this intuition, it has very deep roots because we are surrounded by classical phenomena. We perceive classical phenomena continuously and for free. We don't have to pay anything. That's what we see all the time. And here comes Morpheus again. This ontology is postulated. So non-contextuality, it's a characteristic property of the classical ontology. But nothing prevents us from thinking that it could happen differently. And this is typically what we see. Sorry, I was going on quantum phenomenology, but before I intercalate our postulate 0, which is that we are going to deal with classical contexts. So by definition, in our approach, a context will be classical. The context will give rise to repeatable events which do not depend on potential contexts they could be embedded in, nor on the system they may contain. So these repeatable events, they are eligible to build a non-contextual state, and that will be the state of the context itself, okay? All this to say that contexts are classical, and in an experiment, our measuring devices, they will be classical. That's a postulate, okay? This week is a postulate. Next week won't be a postulate, but this week it is a postulate. Now, what happens if we switch to quantum phenomenology? So we are going to do exactly the same thought experiment as before. I'm going to consider a system and a context. And I'm going, since contexts are classical, I'm able to change the state of the context. So say I can switch from the state C1 to the state C2. what we know from quantum phenomenology and quantum experiments is that in general, the ID card that we are going to build, meaning the answers to the questions asked within a given context, they depend on the ordering of the question. So in my first context, I will get a yes. Then if I ask my question in the second context, I will get a no. And if I go back to my first context, I will not necessarily get a yes, I can get a no. And well, the example that we can take to justify for this, it's a photon and beam splitters. So I'm going to pick up a photon as my system. The context will be a polarizing beam splitter. The state of the context can be, well, either the basis horizontal vertical or the basis diagonal anti-diagonal, and the events that I'm going to track are reflected or transmitted. This is the ordering of the questions. So I first ask my question in for 0 degree, then 45 degrees, then 90 degrees, and I get this sequence of answers. And if I change the orders of my question, I don't get the same sequence of answers, okay? So this, well, shakes our intuition, right? And starting from this observation, there are three possible, three options to postulate the ontology. The first one is what we could call the naive realist approach. There is a state that pertains to the system alone, just like in the classical world. And there is a context, a villain context that perturbs the state. This is horribly frustrating. This is basically the story of Heisenberg microscope, right? In Heisenberg microscope, we have a particle. We want to know the position and the momentum, to know that we send photons on the particle, and then to know the position, we perturb the momentum. So this actually means that we are never able to capture the whole state of the system we are looking at. And again, that's terribly frustrating, and I don't want of this approach, me. Second possibility, instrumentalist. So here you don't commit. There are no states. It's only preparations and measurements and period. I refuse to say more about reality. There's no risk in there, but that's not what we want to do. The third approach on which I'm going to stop is the contextual objectivist approach, which is based on certainty tracking, basically. I search the condition in which I will get repeatability, therefore certainty, therefore I will be able to define what a state is. And there is a very simple constatation that we can do. One can obtain repeatably always the same answer if I don't change the context. So the idea is to apply the same kind of recipe we did for classical ontology. I'm going to upgrade my ID card into a state because I obtain repeatedly the same answer within a given context, okay? Which brings me to what we call the CSM postulate, the fact that in general, a state labels both a system and the context around. And such a contextual state, to clearly distinguish it from the classical states we are used to, we're going to call it a modality. Just like classical state, a modality is objective. It would exist if no one was looking at it. But it labels a system and a context. And this ontology was dubbed contextual objectivity, again by Philippe, like I guess 15 years ago. And I want to say hello to the cousin here, Carlo, because it's clearly reminiscent from relational quantum mechanics, but here there is, so from what I understood from relational quantum mechanics, we look at relation between parties which of the same, which are the same basically. There is no real difference between the parties we look at. Here there is a clear difference in the sense that we have a system and a context which behaves classically in the first place. I guess we'll have the time to discuss the difference later on. Okay, just to precise a bit the definitions. So within a given context, modalities, they really behave like classical states in the sense that they are mutually exclusive. Within a given context, I get a yes or a no, and period. Within a given context, my photon is reflected or transmitted, and there is no other option. But two modalities pertaining to two different contexts, they are not necessarily exclusive. Typically, if my photon gets transmitted while my PBS is like this, I can say nothing about the photon being transmitted or reflected if my PBS is like this, okay? Right, so the last postulate that I will put on the table is the fact that we are going to deal with quantized systems. So what are quantized systems? Quantized systems, they are characterized by a fixed and discrete number of n exclusive modalities. And n is independent of the context. And the typical phenomenon that we have in mind by postulating this can be the Stern-Gerlach experiment. In the Stern-Gerlach experiment, you interrogate a spin and you get here 6 possible spots. The number of these spots won't change if I change the state of the context, which here is the angle of the Stern-Gerlach. Okay.
Sorry, Alexia, do you manage the question? I got confused. I've missed something. The step between context and modality? Sorry,
between state and modality?
No, between context and modality. You have a modality here. What is exactly modality? Sorry.
In the Stern-Gerlach experiment?
No, in general, what is a modality?
In general, the modality. So in the
I missed
classical
the definition.
Yes.
I think I know what you mean, but I just want.
Yeah, but actually it's subtle, and I so in the classical ontology, what we call a state is the property that appears because we get repeatable events. And in the quantum, in the CSM approach, what we call a modality is the property which characterizes a system and a context that is revealed by repeatable events. Okay. So a photon being transmitted and transmitted and transmitted, it indicates that there is.
No, I know what you mean. I just wanted, I got it. I think I got the definition. The key there is exclusive. So two modalities can be different, but not the same if they're not exclusive. Yeah, that's what it was confusing. Yeah.
Yes. Thank you for the question. Right. So, well, it's a good time for questions actually, because I'm ending the first part of the talk, which is the presentation of the ontology.
Then I think Marco had a question.
Yes.
Yeah, so there is something that disturbs me a little bit. So you say, so the way I understood is that modality are like objective. So you have the system, you have the apparatus, which thing you will measure, for example, and you have a question, transmitted or reflected. And from what I understood, you say that then you have an objective answer, like an intrinsic classical property. What I'm a little bit disturbed is that if I have a superposition, for example, in my I don't know, the photon, and I have a spin. I have a superposition up plus down, and I measure, for example, so I am in the state plus, and I measure sigma z. Then the system is well defined, it's a spin. The measurement axis is well defined as well, but here I can have two different answers in a way. So
yeah. the modality in your case is defined in a specific context, which is not the sigma z, it's the sigma x. If you interrogate your spin in the sigma x basis, you will get a certain answer.
Yeah.
Yeah. So a modality is defined in a context. You get certainty within a given context.
Okay, but then you have to restrict the choice of context. You cannot
Absolutely,
take...
but that's the
Okay.
whole point of the modality, actually. You
Okay.
expressed it differently here, but you just demonstrated that in this mindset, what defines a state is not only the system, but it's also a property carried by the context itself.
Okay, I see.
Where do you
Okay.
find the certainty? You need to indicate the basis in which you are going to measure.
Okay. Okay.
Really,
Thank you.
search for the certainty is the motto. Where can I be certain of something? And then you clearly see that the context participates to the definition of the state. Okay?
Okay. Thank you.
Mauro is next.
Yes, let's take a situation which is paradigmatic, like two entangled qubits. So suppose...
Okay, let's go to entangled qubits.
You take whatever you want for the physical meaning of the qubit, and just to understand how you describe the marginal state of the single qubit, which is a completely mixed state, and the joint state, which is entangled in your language, just to understand better the context and the other notions that you are using in this case. This is a...
So that's a very subtle question. And the glasses to think in contextual objectivity are heavy glasses. So so far we mostly focused on pure state to answer your question. So it's...
But the marginal state, the notion of marginal state, you should have it, I'm saying. You are restricting your focus, so you are changing the context. There must be some way of marginalizing.
I would say with the tools that I put you in the end right now, the best thing that we can do is to purify, so that we can always have a pure state. So talking about the entangled qubits, so say plus minus plus minus plus, the good context here is a global context that measures in the Bell basis. That's in this context that we are going to get a certainty, and the modality associated to the entangled state is defined in the context that corresponds to the measurement of the Bell basis. Talking about marginal state would mean that we are going to that we are going to interrogate locally the spins, which is not the context that corresponds to the entangled modality. And in that case, it is normal that we don't get a certain answer, that we cannot find the certainty, because we are not in the good context.
Yeah, but how can you know in principle which one is the good context? So there is the problem that you must use the...
Absolutely. But so, that's, yeah. That's
and you cannot use the God point of view, right? So that you pragmatically.
Pragmatic and humble, we won't use the God point of view. Does it answer your question? At least what is the gymnastic that we have to do to understand marginal probability in that mindset?
Okay, I think so. I think I have to think about. Yes, thank you.
Thank you.
I have a very small point on the meaning of state, just to understand better. So it seems to me that you want to be somehow realist about the quantum state, but
not somehow. Okay. Totally.
then I think I'm a bit puzzled, because you want to be realist, but you want to be realist about state meant as state of context and systems together, basically. You don't want to be realist about states of system alone. doesn't make sense for you to be realist about just the system, right?
No.
Okay. So basically you can have the same, you can have a state of take, I don't know, this system and one context, and you can have the state of the same system and another context, right? You can have two different
I can't have
the system, right?
I can't have two different.
Cool.
Yeah.
So the states varies from the conjunction of the same system and one context and the same system and a different context. You have two different states there.
Yes, I have two different modalities, absolutely.
Okay, so even if the system is the same.
Even if the system is the same.
Okay.
And here you put the finger on something that is extremely important and subtle. So I need to put my words together properly. Ontology of stuff and ontology of states is there is a mismatch here. I can think that a system exists, but to define a state to this system, I need another guy.
Mm-hmm.
While in the classical mindset, stuff that exists automatically carries the state that goes with. You see?
Yeah.
So there is this, usually there is the same focal point, and here the focal point is different. You see?
Yeah.
So, and that's because of quantum, as we are going to see, this is because of quantumness.
I'm just maybe foreseeing a, not a problem, but a feature of this model that might resemble also Carlos' interpretation. But yeah, maybe we can discuss about that later. So yeah,
thanks.
Clear now, and then we come back to that.
Thanks to clarify. Yeah.
Alexia, may I try a little remark?
Sure.
Yeah, no, one has to be very careful because in this context, as soon as one speaks about a state, one speaks about a psi. One has a psi in mind. So we have the usual quantum formalism in the mind, and I will emphasize that even more next week. So a psi is not a modality. A modality is what Alexia defines. You need both the system and the context. So a modality is a property which is attributed jointly to a system and to a context. And if you think strongly about a psi, it's not exactly that.
So you're realist about states, but not about psi.
Yeah, well, in the usual language, psi and state are the same. If you take a Entanglement book, you start with the state of a system is a vector in an Hilbert space, etc. So there is an identification between a quantum state and a psi. And then when we use usually the word state in quantum mechanics, we think about a psi. So we emphasize that a modality is what Alexia just told. It's a joint property of a system and a context. And if you think a little bit, it's not a psi. I will give more details about that, but be really careful with the words. I think Alexia is consistently explaining what we call a modality. And remember, it's not exactly a psi. There is a subtlety. So I will not explain the subtlety now because it will mess up Alexia's talk, but I will explain it next week. So, but be very careful that a quantum state in the usual sense that is a psi is not exactly a modality, because in the modality, we really need the context.
And that's why I asked you in the beginning of the talk to forget about the quantum formalism. The psi was also in the quantum formalism. Forget this. We look at phenomena right now.
Yeah, because one of the things. So while I was reading your papers, I was reading a lot of times realism about state, and I thought that was a difference with Carlos' interpretation, because he spent a lot of time arguing that we should not be realist about state. But I think Carlo might say that better than me. But anyway, now I understand that actually there is no difference. Maybe it's just verbal difference, but actually you're saying the same thing in this, as far as I can see. But again, we can come back to that later. I think Marco has a finger there.
Yeah, it's just that now I'm confused with the thing we talked about superposition, because with the example earlier on I gave with superposition, because what I understood is that then the context must be defined so that the answer is certain.
Yes.
And for me, it's totally equivalent to say that you just provide the weight function. I don't see where
another
will be
way
the difference.
another way to answer this is in the modality there is the context.
Mm-hmm.
And the way to answer mathematically, I didn't want to talk about math, so Philippe started to talk about psi, so I'm going to try to bounce back on this. But the psi is an eigenstate of something, right? And that's this something that is the context. So that's why you get a certainty. The certainty is related to the context as well.
Okay, but
okay.
Okay. Well,
it's your
maybe
puzzle.
I will ask, like,
It's your puzzle. It's normal because
you don't need to have a pure state to have a precise property. You may have it also in a mixed state. So, and purity cannot be falsified. So it's an ontology that is not really out of the theoretical value of quantum theory, because it can't be falsified. Actually, this is something that people don't know. Purification by itself, there is a theorem, cannot be falsified.
What cannot be falsified? Sorry, I didn't.
So you need a test. You need a test that if the falsifier occurs, then it's falsified. So you make an assertion, say something must be true, and if it is true, if it is false, something will happen, and then this will happen. Falsifying is not a dichotomic test in the sense that if it doesn't happen, you don't know anything. If it happens, it's falsified. Like in the Popper.
Yeah, I get logic. Popper, but here.
So purification is something which is not falsifiable. So is also always an assumption, or you know the state because you prepare it.
But again, here we are not in the theory. We are providing an ontology, and like I said, ontology is postulated. So if it's postulated, it cannot be falsified.
I totally agree with you. I know that you have a different perspective.
Yeah.
It's not saying that. I'm not criticizing.
No.
The ontology does not mean it's falsifiable.
Absolutely, absolutely. Okay. Maybe.
If you want to go ahead, or I can wait? It's not. You prefer?
Qu'est-ce qu'il en dit, Christian? What do you think?
Well, I guess it depends on how long.
So just to precise, so that's the presentation. I put the food on the table, and then I'm going to cook.
Okay.
Because randomness is cooking. So and it's the second half of the talk.
I think
maybe just a finger on this discussion here.
A finger gone. Surely.
Yeah. I was trying to listen to your answer and the questions, and maybe you can sharpen something in your putting the argument on the table. Which one of the two? Because this is a Dariano question and others. If I have a system in a context, a photon in a Stengerlach in a certain direction, I understand what you mean by certainty, and understand what you mean there's a certain number of discrete modality in that particular context, so on and so forth. But I hear you talking after a while. I mean, in the language of standard quantum mechanics, after measurements. I think the question that Dariano was raising in others is that what about before? Suppose that I just consider a context and I consider a system, and let me imagine that before it was I had information about another context, or even it was correlated with something else, entangled with something else. So our common intuition is that until I measure, I use standard quantum language until I measure for the moment if there is a notion of a state, there isn't a notion of state within this context for this system. There is somehow a larger notion.
Yeah.
So when you talk about certainty, you're not talking about certainty just given the system and you talk about potential certainty given a system in a context. Is that the case?
Yes.
Okay.
Yes. And you asked what happens before. Actually, in the mindset of CSM, there is always already a modality.
Yeah, there's another model. Yeah,
yes.
You're in another modality. You're changing modality.
There is always already an event, something that is recorded somewhere, and there is a change of context, and there is a random change of modality. I mean, this brings me to the second part, but yes, it's there is always a context in which the modality is realized. Absolutely.
Maybe it's just the time to ask you, Alexia, my usual question. From an ontological point of view, then you have these modalities, and then you have characteristic of these modalities, namely that they can be actualized or non-actualized. And my usual question to you is what are non-actualized modalities?
Yeah.
Because in your writings, you also want to distance yourself from potentialities and these kind of things, which...
Yes. So the best way to answer is again to come back to the classical way we build a state. In the classical way we build a state, I have this ID card that contains repeatable events or phenomena. And these repeatable phenomena, which are actual, they point towards a state. They are the clue that there is a state. And this state in the classical realm pertains to a system alone. But these states can give rise to a phenomenon that will be recorded or not. That's the same for the modality. But the way to obtain repeatable and certain phenomena is to specify not only the system, but also the context. So,
Alexia, I think this will clarify after the next step. So I think you should move forward.
Okay, yes, absolutely. Well, so we keep that for later because actually you're asking what is the change of modality, basically. And what's happening inside an interferometer. And this is something that we can consider a bit later. Okay, so I have actually here put stuff on the table, and I'm going to summarize the point we have reached. With the CSM postulate, what we have now in the hand is a critical and at the same time textbook, because if you open this guy here, this is what you are going to find. This is the partition of the world that is for undergraduate. This is a context around a quantized system that is characterized by n exclusive modalities. What I'm going to argue now is that this partition of the world, it is sufficient to account for quantum randomness. Actually, it is a cause of randomness per se by itself. And since we have the quantum randomness, now we know what the quantum formalism is good for. And next time, so in Philippe's talk next week, when we go to math, he will show you that this partition of the world is somehow necessary. But for me today, I'm going really to focus on this, the fact that if we admit that there is this kind of partition, which defines a certain ontology, I can get randomness and quantum formalism at the origin, okay? So now I go to randomness. And before talking about quantum randomness and its specificities, I want to recall a bit what is the origin of classical randomness, which is the one that we know in the everyday life. So classical randomness, it's usually very for the layman, physicist, and everyday life, it's due to some ignorance. And it's the ignorance of what? It's the ignorance of the state of the system. I'm playing cards. The cards are not, the cards are on the back, so I don't know if there is a queen or a king behind, but there is a queen and a king that define the state of the card, and I don't know this state. That's why there is classical randomness. So the truth is hidden, the state is hidden. And classical randomness, it vanishes with information. It is somehow subjective. And if I knew everything, there wouldn't be randomness anymore. So there is also this idea that basically in the classical world, randomness is something, a sign of weakness, right? We could do better. And if we were God, we would know everything, okay? Statistical physics. There are two big theories of randomness. There is statistical physics and quantum mechanics, and I will compare the two in the end. But statistical physics, it relies on classical randomness. And when does this randomness appear in statistical physics? It appears when we go from the micro to the macro. Okay? It appears with a coarse graining. At the microscopic level, the states of the systems are perfectly defined, but I have only access to the macroscopic variable. So I lose information while I am coarse graining, and eventually it gives the second law of thermodynamics. But there is this idea that a good vision is at the microscopic level and the truth is below. And that defines the goal, basically, of statistical physics, describing the world at the proper level where everything is known, and reconstruct the classical level by averaging and coarse graining. Okay, what about quantum randomness? So in the first interpretations, and again, I come back to Heisenberg microscope, because actually when I was taught quantum mechanics, this is basically what was told me to justify for the randomness. Randomness would come from some irreducible interaction between the studied quantum system and the experimental context. So if you like, it's some sort of irreducible coarse graining that is at play here. And the feeling that it conveys is that the system has a hidden state, and the state is perturbed, just like I was saying in the beginning with the naive realist approach. And okay, so the challenge to understand randomness is that our intuition on randomness, they are based on non-contextual states here. What I'm going to do in the rest of the talk is to understand what causes randomness in a contextual world. And actually the goal is to relate randomness in the contextual world to quantization, to make randomness a consequence of quantization, to basically answer the question, but what is quantum in quantum randomness? So that's the story now. Again, I come back to the two claims, because that's what I'm going to build the approach on. We have this critical partition of the world. So we have a classical context around a quantized system that is characterized by n exclusive modalities. And I've claimed that the partition of the world is sufficient to account for quantum randomness and quantum formalism. So now I'm going to explain why. And to do that, I want to come back to the switching from classical states to modalities. On the left, you have what we have in the classical phenomenology. In the classical phenomenology, what we have seen is that context, they are always there, because I ask a question always within a given context, but the fact is that they can be forgotten in the end. And the clue we had from that is that the ordering of the answers that we get do not depend on the order of the questions, right? So the contexts are there, but they can be forgotten, which allows me to define a state which depends on the system alone. In the quantum realm, what we have is that contexts, they are always needed to define a state, because that's where I get my certainty. That is the quantum phenomenology we have seen together. So this conveys the idea that contextuality is somehow universal. States, they always show up in a given context. But in the classical realm, the contextuality is soft, because I can forget them. In the quantum realm, the contextuality is hard, because I can never forget them. And the claim, what I want to justify now, is that to go from the soft contextuality to the hard contextuality, the key is to use the quantization of modalities. The reason why we go from there to there is that with quantized systems, modalities are quantized, and that's why contextuality becomes hard. So why is that so? Again, I'm repeating myself, but let's hope it's the basis for pedagogy. My claim one is that starting from the universality of contextuality and the quantization of modalities, I can show that contextuality becomes hard, which brings me the non-commutation of the questions, the unpredictability of the answer as the context changes, and this is what we call ontological randomness, which is not...
What does quantization mean here, precisely?
Quantization of modalities, it's our second postulate, where we say that with quantized systems, there is only a number n discrete finite modalities.
Discreteness, yeah.
Yes, discreteness. Yeah, I never know if I should say discrete or quantized. So you suggest to say discrete instead?
Quantized means everything. It's used
Absolutely.
for all sort of variety. Discrete a little bit less.
Yeah, okay. Well, in my former version of the talk, there was discreteness everywhere. So, well, do the transposition, please, if it makes more sense. Thank you.
A little comment, Alexia.
Oui.
Yes, so the main point is that there are mutually exclusive modalities in a given context, okay? So in a given context, the different answer you can get are mutually exclusive modalities. And the main quantization postulate is that in finite dimension, the number of mutually exclusive modalities is the same in all contexts. This is our quantization. You see, it's a very powerful statement, because if I change the context, I will have n results which will be different in general, but the number n will always be the same. And you guess that at the end it will be the dimension of the Hilbert space. But this is a very strong statement. And for instance, you may have non-commutativity, but in psychology, for instance, things are non-commutative, but the number of mutually exclusive answers has no reason to be always the same. If you impose that it is always the same in all contexts, what we really call quantization, and this is a basic tool to rebuild the formalism. Okay, I stop here. Does that help?
Yeah.
I get used to it, so it doesn't help for me. Okay, so how do we prove that? The way we prove that is to come back to our operational approach, where we build the ID card. Okay, so I'm picking up a quantized or also called elementary system that is characterized by two possible exclusive modalities, this dimension of the Hilbert space that Philippe was mentioning. And I'm supposing that I have the ability to change my context state from C1 to C2. Okay, so I do my little experiment. In the context one, I can get two possible repeatable answers that correspond to my two possible modalities. If you want to fix the ID, just think about the photon that I interrogate in this basis or this basis. Then I go to context two. I get two other repeatable answers, which corresponds to two other exclusive modalities. And then I'm wondering, if I go back to context one, can I predict the answer with certainty? And so here you already have the answer. If it was the case, it would mean that I have 4 exclusive modalities that correspond to all the answers that I can have in context 1 and in context 2 at the same time. But we have said that the system was defined by 2 exclusive modalities only. So here we are violating the bound. So the fact is that because of the bound on the number of modalities for my system, I cannot predict the answers with certainty, when I go back to context 1. Okay? And this is very strong, actually, because we just shown that randomness is necessary here. Randomness is a consequence of contextuality and on the bound, on the number of modalities I see. And for the little story, that's the reason why I bought CSM. Because like I said before, I was always very perturbed and very frustrated by the justification of randomness by Heisenberg microscope argument. I don't feel like saying that nature is random per se. And this explains me why actually randomness can be justified by quantization and a bound. So for me, it was very, very satisfying because it really puts quantization back in the heart of the theory. Okay, that was for the little story. So
Alexia, sorry.
Yes.
Just after this proof, could you comment again what's different with the classical? If it was a classical system, how would that change this
So
proof?
if there was a classical system, there wouldn't be a bound on the number of modalities. And if you don't have this bound, you can keep concatenating contexts and you can keep extracting information. I'm using this wording, but before it was used by Zeilinger. For him, quantum systems are defined by the amount of information I can extract from them. So that's another way of seeing this. In the classical, there is no such bound. So you can concatenate context and fill your ID card as much as you want.
Mm-hmm. Well, Alexia, sorry, jumping in. Yes, I agree, but that's not sufficient. I mean, there are classical discrete systems. You need the bound on the number of states, but also you need the fact that there are different contexts.
Yes, absolutely. Yes,
the discrete systems also have a bound in the modalities, but they don't. They have only one context, so to say.
True.
So it's the two together that force the.
Together, absolutely.
Yes, what you say, Carlo, is really important. Yes, this is the main idea. Alexia, I like to say there are more questions than answers.
Yeah, and I'm coming to that point. But yes, it is absolutely related. Well, so I'm going to insist a bit on the logical sequence here. So what did we have? We have universal contextuality. We have a system with discrete modalities. And as Carlos says, we have the ability to change the context state, which is very important. And we arrive at a situation of conflict where we have less repeatable answers allowed than possible answers to possible questions. And this is because of this conflict or critical situation that we get necessary the randomness, which is manifested by the non-commutation of the questions that we see and the unpredictable answers, which are core quantum features. But you see, we obtain these core quantum features from the phenomenology, contextuality, which is a result of a phenomenon that we see in the quantum realm, and systems with discrete modalities. And I like to say that we obtain core quantum features without putting any bit of mathematical formalism in there. It's just reasoning and observation. So it's very economic as an approach. And by the way, this gives us the goal of the theory, because now we know what quantum physics is good for in that mindset. It's to describe the random change of modality when we change the context. So randomness is in the heart of the theory. It is what the theory needs to describe properly. It's not to come back, but I will come back to the comparison with the statistical physics. Randomness is not a weakness that we want to eliminate. It's the feature on which the theory is built. Okay, just a parenthesis. What about the quantum formalism? I anticipate just a little bit on next week, but so here we see that with this very economic set of postulates, contextuality, quantization, and ability to change the system state, we arrive to randomness. The ingredients that we need to add to arrive to the quantum formalism, and by quantum formalism I mean Born's rule, Hilbert space, unitarity, etc. It's the ability to change the context state continuously. So if you add this ingredient, you can demonstrate, well, or reconstruct, or Philippe is going to amend if I'm using too strong words, but I like to say that it's a heuristic derivation, that we can have the quantum formalism with very simple and basic arguments like this. No intervention of Philippe, so I didn't say any crap. So
Alexia, I just have a little question.
Yes, please.
What you call hard contextuality is here, is it in some paper what you call extra contextuality, or is it different? No.
Extra contextuality, you will get this food next week.
Okay.
It's describing, it's a property of modalities. Here, hard contextuality is just the difference between hard and stuff is, like I said, it's what defining the classical ontology we are used to, where state pertains to system because you have forgotten the context, because you can do it, and the hardware, which is the quantum phenomenology, where you cannot forget the context to define your state.
Okay. Thank you. Yeah, maybe one word about extra contextuality that I will explain next week is about the difference between a modality and a usual quantum state. A psi. So a modality is not a psi, and this is due to extra contextuality, and I will describe that next week.
Okay, thank you.
Okay, there is something I want to discuss before finishing. It's the quantum classical boundary, because if you paid attention, when I go from soft to hard, because of the quantization of modalities and the existence of this bound, this has the flavor of a quantum classical boundary. It seems that we can go from classical to quantum ontology by taking some sort of continuous path. So I want to comment a little bit on this. And first, I need to give back the quantum classical boundary to who most worked on it. Which is Jurek, who described it a lot in the 90s with the theory of decoherence and stuff. And in Jurek's approach, the idea is to really start, the postulate is not phenomenological, it's mostly mathematical. We start from quantum systems whose evolution is ruled by Schrödinger equation, and the game is really to let the classical world emerge by averages, by coarse graining, in an approach which is really inspired by statistical physics. Actually, it's really the same bottom-up move within the same reductionist mindset. And the goal, the ultimate goal, is to get rid of this awful measurement postulate that ruins the beauty of the theory. You probably noticed that in the CSM vision of the things, it's absolutely the other way around. In CSM, everything starts by the classical. There is a classical context that is always already there. There is a first modality that is always already there. And basically the measurement postulate, it's embedded in the approach. It's constitutive of the approach. So this is a big microscope with a system that is a big mammoth here. Now, what we do in CSM is that we reduce the number of modalities of the system up to reaching this quantized system and this critical partition of the world that I have described before. So you see the move is totally different. It's not bottom up. Randomness does not emerge from the bottom up. It's top down. Quantum randomness, it appears. So like I said, because there are less repeatable answers than possible answers to all the possible questions, which appears when I reduce the size of my system in a top-down approach. And this mismatch, it is only possible if there are both a system and a context. So the context system interface, it's a condition of randomness, and it's a condition of the motivation of the formalism, right? So here I want to comment the fact that so the fact that the context is always already there, it's pretty reminiscent from Bohr's approach, right? It is typically Bohrian mindset. And pretty often it was confused with basically operationalism. We can't say anything if this is not measured, and that's it. So the measurement postulate, its necessity, it's basically practical. Here, it's not only practical, it's randomness is here because there is an interface between system and context. So it's not only practical, it's really, Philippe wants to say something.
No.
No, I heard some. Because when I start talking about Bohr, he said many things, so we can always make mistake if we try to cite him.
Anything. Also, we were told, Alexia and myself, many times that what we are doing is just Bohr's philosophy. We don't agree with that. It's close, it's the same family. We are cousins with Bohr, but we are not Bohr. I think there are really very significant differences, but it's clearly the same family of thinking. And this is just what Alexia was telling, so I'm perfectly fine.
Actually, I don't ever heard any discussion on the origin of randomness in Bohr's writing and stuff, which is something that here is due to the presence of the context and the quantization of the system. So that's one of the one big difference.
So maybe about Bohr, another big difference is that a major issue for Bohr was complementarity. And here you see, we never speak about complementarity because it's too poorly defined in our. So and Bohr, as Alexia told, many different things depending on time, on periods, on circumstances. So we are clearly in Bohr's family. We are Bohr's grandsons in some sense, but I don't think it should not be confused. Well, okay.
Right, yeah, so I love this top-down. Sorry if I pollute this with, but to me, it's something that is very important. So again, the context is always already there. The system will never swallow the context. So in other words, there is no wave function of the universe, right? We always need the system and the context to start playing with the quantum formalism and quantum randomness. There is no emergence of the classical from the quantum. So this approach, it challenges classical reductionism. You play with the bipartition of the reality from day one. So that will be my conclusion slide, because I want to conclude by comparing again statistical physics and quantum physics à la CSM, and compare the two sources of randomness, basically. On the left, you have like I said, statistical physics that is playing with epistemic randomness. Epistemic randomness is due to the ignorance of states which are non-contextual. And this randomness, it comes from an information loss that appears during the coarse graining from the microscopic to the macroscopic in a bottom-up move. It's somehow not really fundamental, because again, if I was God, I would know everything and there wouldn't be any randomness, putting aside the problem of the chaos and stuff. So in statistical physics, it is perfectly compatible with a reductionist approach. We deal with identical systems, and the goal of the theory, once again, is to let the macroscopic world emerge from the microscopic by multiple coarse grainings. On the other side, you have what I just presented you, which is ontological randomness, where you have some unpredictability that is certainly not due to ignorance, but that is caused by contextual and quantized modalities. And it appears while we lower the system side in a top-down approach, and this is a fundamental randomness. And so the approach is non-reductionist, again, because it requires a system and a context to have a meaning. And the goal of the theory is to describe this random change of modality at the change of context. And the way to do this, again, will be presented by Philippe next week. So I come to a bit of conclusions. And these conclusions, I'm going to list a certain number of reversed hierarchies that have been implemented by the CSM view of things. I have reversed in this talk the hierarchy between ontology and formalism. Pretty often, quantum formalism is put on the table and then we try to figure out what we are talking about. Here we played the other way around. We started with phenomena and then next week there will be the formalism. So it's somehow reversed with respect to more usual approaches. We put the event first and psi is second. I'm going to comment this. We put non-unitarity first and unitarity second. And we put discreteness first and interferences second. So what does it all mean? Well, I have commented the fact that the formalism will come next. So I guess this is an idea that that you get, because again, there was no mathematical formula in this talk. And yeah, so this is also something I said, but I want to insist on it, is that we didn't need mathematics to arrive to the core features of quantum physics, which are ontological randomness. Well, I didn't talk about non-locality here, so I keep that for questions if you like. But yeah, again, we need phenomena and concepts to arrive to the motivation of the theory in the end. Phenomena first and psi second. So what I wanted to say here is that the CSM approach, it's based again on certainty tracking. It's based on repeatable, certain, and actual events. What is real, it is the modality, not the hidden wave function. But the price to pay is that the modalities, they are contextual. Non-unitarity first, unitarity second. So here it's a thing that is a bit postulated in the sense that we have not moved to the formalism yet. But what you will see next week, again, it's that the fundamental quantum event to be described by the theory, it's the random change of probability. It's the random change of modality, sorry. So it's a probability law to write down. Which is usually described by something that is non-unitary, and it is opposed to unitary transformation that are just here to describe the change of context. And this is a very different approach than, for instance, people of the many worlds who would put unitarity as the fundamental the fundamental way to let systems evolve, and non-unitarity is something that you want to get rid of. Okay, here non-unitarity comes first, and unitarity is derived. It comes after. Quantization first, interferences second. Well, this is bad as a concluding slides because we didn't see the formalism. So I guess I don't want to comment this too much. And I come to the outlooks. So the outlooks is that, so in the approach that I've presented you today, the measuring device was the context. The idea is really to be able to generalize this approach to the case where the context is something which is not necessarily a measuring device. So basically replace a context by an environment or by something that we know in quantum open system that plays a role of measuring apparatus without having been designed as a measuring apparatus. For philosophy, I think but I'm not a philosopher, so I let that to philosophers of the audience, that this idea of rethink epistemology versus ontology given contextual objectivity is something that is very stimulating. And this has to see with the question that Christian asked, the fact that we can think systems independently of the state they carry or not. And the fact that there is this mismatch or this lift of degeneracy between stuff and states, this comes from the quantum bound on the number of modalities. So I think this is something that would be nice to investigate more. And well, this is my personal little baby of this, is that the approach is fertile because what we saw about quantum randomness can have very nice consequences in terms of thermodynamics. I spent some time to compare statistical physics and quantum physics because they are both based on different sources of randomness. And the game that I'm playing with part of the audience here is to basically revisit thermodynamics if the dice is quantum and not classical. And this ends what I wanted to say today. So yeah, thank you.
Thanks a
I
lot.
have many comments.
Yeah,
Whether you
sure.
think it's a good one.
you can go. Yeah. Please, Carlo.
Well, first of all, this was wonderful. Thank you very much. I mean, Alexia, this was a brilliant presentation, and I took a lot of note. I think you present with great clarity, and I mean, I look forward for Philippe to go to do the technical part. Sorry, Philippe, for that. There is certainly a huge amount of similarity with relational quantum mechanics. You said we're cousins. I think we're brothers, and more than that. So I want to comment about that, and of course, I want to take away any question about priority, because this is not about priority. This is about. I mean, you and Philippe have been thinking about lines. I and others have been thinking about parallel lines. I think what's good is what we can learn from one another. The overall philosophy is incredibly the same. I would say the notion of state, the fact that discretization it's the key, and the fact that there are more questions, as you like to say, than possible answers is the origin of randomness. In fact, H bar is the same. The H bar is what determines the discreteness, and the H bar is what's coming the commutation relation. It's the same H bar. It's not two different things. And I could go on and on with similarity. So I want to focus on the differences, because that's where I can learn something, or we can learn something from one another. And the difference seems to me is not on the notion of state, which is the same. It's not on the notion of. It's not on the contextuality, which is the same. It's not on the notion of where probability comes from. It's not on the notion of what is the. I would say the ontology is extremely similar. The difference is the notion of context, of course. So I've been trying, since I read your papers, to see how does the notion of context play a role in relational quantum mechanics and vice versa. And it seemed to me that it adds something, from my perspective, which always confused me in relational quantum mechanics. And perhaps it misses something. So let me tell you the two aspects of it. Adds something because I could use your slides and 95% of what you said as a presentation for relational quantum mechanics, just literally everything. In fact, I will. But a context it's a subset of the world which is made by systems in relational quantum mechanics. Now I'm saying words from relational quantum mechanics, not from what I heard from you, which themselves can be quantum systems and themselves may have their own context and their own description and so on and so forth. So in relational quantum mechanics perspective, I would say is the same, but the context is just another system or a collection of systems, because a collection of systems is still a system.
Yeah.
And that's connect. But of course, this is a reductive connection, because that's not really what the context is for you. Because if I take a Stenger-Lag apparatus, I throw it away and I put another thing that measures the same thing, that's the same context. While in relational quantum mechanics, a different system. So a context is much more than that. It's a sort of an equivalence class of possible other systems, which is much more than, because it's something which is in the belly of the system itself. Is the way the system itself can interact with something outside. Is a possible context in which a system can be. For you, a context is the same whether I'm measuring the same spin with two different apparatus. So the notion, what I'm saying in a confused way is the notion of context seems to me to makes more clear something which in my own old papers on relational quantum mechanics was not clear, which is that, I mean, in my original paper, I had the same postulate about discreteness, the second postulate about the fact that you can ask new questions, so this great probability. But I had a notion like, given a system, there is a set of answers you can ask to it, and different set of answers. And that's much more closer to what a context is for you. So for you, a context is both the set of other systems that interact with the system and the possible answer you can ask.
Yeah.
To the, so that's, I think I find it a very sharp notion, which it was far more confusing in relational quantum mechanics. So that's, for me, something I'm learning. What I find still missing, but you sort of mentioned that, is that to the extent in which a context, it's an abstract possibility of in which physical context, let me say physical context and context, in which physical context can be, that's only pertaining to the system. But concretely, a context then is made by the apparatus. In fact, you repeatedly mention apparatus mention. And a key point of relational quantum mechanics is that the context itself can be quantum mechanical, because the apparatus can be in a superposition. And if I don't see the quantum property of the apparatus, it's not because they don't exist, it's because they are small, they are suppressed by the coherence, I don't see interference between different states of the apparatus, but they're there. So the strong, I'm with you 100% of what you say, but the strong realist overtone that you put in this story, I think it needs to be tempered a little bit, because it's true that the system in a context has a modality, period. But concretely, this is a system interacting with apparatus that has been up, but think of Wigner friend, I can jump out and in principle still measure interference effect between the spin up and apparatus measure spin up, and spin down apparatus measure spin down.
Carlo, the in principle is a trap.
No,
Yes.
I think, no, wait. I want to be, I'm putting my finger here. I don't think it's a trap. I think that either at some point quantum mechanics is wrong, so it's a fact. I think it's a fact. Is it that with sufficient capacity, I can always see interference, or at some point the interference disappear? And so if there is a difference, but I would expect you to tell me that you don't think there is a difference.
Well,
Are you really thinking that apparatus are
may I ask you a
classical,
question?
even when observed by, don't they themselves are made by physical objects that have a context? That's where I if anything, I see a distinction. All the rest, this is a key point, but all the rest, I think it's we're on the same ground.
So if I reformulate what you question is the validity of the postulate 0, where we claim that contexts are classical.
Yeah.
No, may I ask you a question, Carlo?
Well,
if I
just
you...
one second. Let me ask. Yes, or what do you mean by a context being classical? So
by context being classical, we mean that if I'm applying the same thought experiment, like I'm trying to see which kind of state, which kind of ontology apply. So I embed my context in another context. I do my ID card, and I realize that the order of the question does not influence the kind of answers I get.
Yeah.
And that's
yeah. So I would say I agree with your postulate 0 only in the following sense. Postulate 0 is not true in the world, but to the extent in which it is a very good approximation to a very large number of situations, postulate 0 plays a role.
But then I answer by another question. What is your initial postulate? How do you describe it? Is quantum formalism first, or because I mean, what I try to show in the approach of today is that if we have classical context, so if I take postulate 0, postulate 1, and postulate 2, I get the randomness, and then I get the quantum formalism, which is the follow-up. Here, if we say that contexts can be prepared in superpositions and stuff, it means that the quantum formalism is there before I say what a context is.
No, not at all. No, not at all. You keep everything. The only thing you keep everything you said. The only thing you don't keep is a strong realistic tone. So the fact that a spin has spin up, it's true. It's a fact of the world relative to a context, relative to an apparatus.
Okay.
Period. I'm with you. It does not mean that it is also true with respect to Wigner frames for whatever possible measurement Wigner frame would be.
Carlo, may I ask you a question? It seems to me that it will sound esoteric, but I'm sure you will understand. You are thinking within type 1 quantum mechanics, and type 1 quantum mechanics is wrong.
What is type 1 quantum mechanics?
Come next week.
Algebraic quantum theory, you know, all these things with C-star algebra, etc. Which are, you know that very well because you wrote papers with Alan Kohn on this subject many years ago.
For Neumann algebra type 1, you mean? What
yes, for Neumann algebra type 1, which is standard quantum mechanics, is just wrong. And I think it's really, because we learn, we are always thinking within this type 1 quantum mechanics where you get universal quantum superposition, etc. But it's simply wrong. It's not sufficient. It's not enough. The mathematics is inappropriate. And this is sort of our current conclusion.
So Philippe, if I may, what do you mean by it's wrong? It doesn't apply to the world?
It doesn't fit with nature. It's overly restrictive. But von Neumann told that in 1937, I think.
How does it connect with what we were saying? I don't see the connection.
The connection is that if you include, you know, von Neumann algebra, like type 2, type 3 especially, you have unbodied system, you get super selection rules, and it does things which are much, much closer to what Alexia tells. Because you don't have any more universal quantum superpositions. They are destroyed because if you have infinite number of particles, mathematical infinity, not physical one, then you get all kinds of different rules which basically kill the unitarity. And you are done.
So what you're saying essentially is that you deny universality of quantum theory.
No, of type 1. This is a big, big mistake. I deny the universality of type 1 quantum mechanics. you must use algebra, this algebraic approach with type 3, because you need unbounded. I think it's a way to answer, I will tell more about that, to answer what makes a context a context. I think what makes a context is simply that it is unbounded. And it is physically unbounded, which means that mathematically you must be able to take the limit of an infinite number of particles within the formalism. And in type 1 quantum mechanics, you cannot do that because you explode the Hilbert space, it's no more separable.
But it's an approximation, right? We never make experiment with an infinite number of particles. We make an experiment with 10 to the 32 particles.
Yeah. You know, I discussed that hundreds and hundreds of times. You should not mix the physics and the mathematics. So the basic split you have to do first is to separate physics from mathematics. And for me, physics is physics. Nature has some reality. And mathematics is a language we use to describe nature.
Yeah, so in physical terms, do you think that there are objects which are absolutely classical, that don't have quantum properties?
No, it has quantum properties, but if you use unbounded systems, you have to describe them by macroscopic observables, for instance, and they all commute. So this exactly answers your question.
If you are saying is wrong in the sense that, for example, non-relativistic quantum mechanics is wrong, then you need quantum field theory, and in this sense is wrong.
No, but so,
then every theory is wrong, because I'm saying even general relativity is wrong because it's not quantum. And
no, it's not well. I don't tell exactly.
You have to keep a theory within its own context, because you can't say that it's wrong.
What I say is that type 1 quantum mechanics is good mathematics, is consistent mathematics, but it's not a good description of nature.
This is the one that is used all the time on papers, actually.
Yeah, yes.
Very. Practically never it is used type 3. Type 3 is something for
mathematicians.
For mathematicians, exactly.
Yes,
there is not a single student who knows what is type 3.
Yes, but I think physics is losing a lot of stuff and getting lost into endless questions because we as physicists are not unable to manage type 3. I'm not an expert on type 3, but I know enough on type 3 to tell that they can answer many questions which always look like questions, but which are not misunderstood mathematics. But von Neumann told that, you know.
I don't know when von Neumann said that. Von Neumann said also wrong things, so it doesn't mean that von Neumann is always true. I'm saying there is a point. A theory is wrong when it's contradictory.
Yes.
That's the only. But it's contradictory inside.
Yes.
To say it's wrong. Wrong is a logical assertion.
Wrong or right. Logically.
So it has nothing to do with falsifiability. It's something different to say that the theory is wrong.
Yes. So
okay. Then let me say where is the contradiction, logical contradiction inside type 1 quantum theory? What is it?
So it's not really a logical contradiction. It's the fact that I tell more. Type 1 is unable to manage unbounded systems.
Yeah, which is the thing that you do all the time in the lab.
Yeah, and then you add the projection postulate, and you have then you add phenomenology. It's exactly what you are doing. It's very different to, you know, I'm an experimentalist. So either you adopt a phenomenological point of view and you are fully happy, just what. But now, if you ask fundamental question, what about the mathematics? Why do I have these universal superpositions? For instance, Schrödinger cats or many worlds or things like that. It clearly contradicts experiment. So what is that wrong?
So I don't think they contradict experiment in any sense. Schrödinger cat doesn't contradict experiments because it's the quantum mechanics I learned from Alexia very clearly, but I also learned from quantum mechanics books doesn't predict that I see superposition, predict I see interference. This is something very different. But let me show. I don't want to resolve that. I don't want to say who is right. I want to only put the finger where the difference is, Philippe. If I hear you correctly, and the difference is, I don't want to say what we want to do. The difference is that in relational quantum mechanics, one of the starting points is that every object of the world, everything in the world behaves quantum mechanics. While, if I hear you correctly, but I might not hear you correctly, you're saying, you and Alexia saying, I can make sense of all of that, provided that there are classical things that behave classically, the context. I need things that behave classically.
Yes.
Yeah.
Is that what you're saying?
Yeah.
Yes, but after that, I look for mathematics which agree with that, because standard type one.
Okay. So this is the difference.
Something behave classically. They tell me
this is the difference. So in a sense, I always said that relational quantum mechanics is very close to Copenhagen interpretation in the sense of Bohr, not in the sense of Heisenberg. I think, Alexia, you're right that Heisenberg had this idea of the origin of randomness, but I think Bohr convinced him that he was wrong already. And definitely EPR convinced everybody that that way of looking at the origin of randomness was wrong. But yours is even closer to Copenhagen, because there is a classical world in a sense, and quantum systems behave quantumly, contextually with respect to a classical system. So it's really, really closer to Copenhagen. So that's a big difference with relational quantum mechanics. Relational quantum mechanics want to make everything, in a sense, more democratic. It's not the quantum world itself might be quantum with respect to something else.
We agree on
that's the difference.
Yes. But then I'm stuck because people ask us this time mainly this question many times: what makes a context a context? How can you claim, to which extent can you claim that there is a context different from systems? We certainly agree that a context is made with atoms, but exactly what you told before. With a Stern-Gerlach, I can change a Stern-Gerlach, I will make still a spin measurement. So it's not the color of the paint or the shape of the Stern-Gerlach. It's basically just a magnetic field gradient which matters. And so what is this magnetic field gradient from a quantum point of view? So this is what people call a macroscopic observable. And you can define such things in the algebraic theory. You can summarize the whole stuff of your Stern-Gerlach in the relevant property, which is just actually the magnetic field gradient. And so it's a macroscopic property which involves myriads of atoms, because there are zillions of atoms in the Stern-Gerlach, but you are able to manipulate this quantity as part of your formalism. And type 1 quantum mechanics does not allow you to do that, while algebraic theory does. You can mix up things which are unitary evolutions within a, and also commuting quantities at the macroscopic level. So I don't, I'm not, the big trouble is what Moreau just said. It's very, very mathematics, and the mathematics are just awful because it's basically algebraic topology. But I think physics is really missing to include these tools in our framework, because we are always stuck to what I call textbook quantum mechanics or type 1 quantum mechanics. We always assume that everything should be unitary, which is simply mathematically wrong. If you go any kind of unbounded system, you kill unitarity mathematically. Just take n qubits. The n qubit, you make n go to infinity. So what is the dimension of the Hilbert space? So it's 2 power n. So will that go to a countable? So n will go to a countable infinity because it's a number of particles. So 2 power n will go to a countable infinity. What's your answer?
Yeah.
My answer is that I don't think there is ever a situation with an infinite number of particles which concerns us.
Yes, it's about mathematics, not about physics. It's about managing limits. And what I tell you, because so it was proven by Cantor more than 1 century ago. If n go to a countable infinity, 2 power n go to an uncountable infinity, like real numbers. So if you have an uncountable dimension of your Hilbert space, 2 power n, it becomes non-separable. So everything blows up.
So we have started next week's talk.
Yes,
actually.
no, but you know, the trouble, it's not the main content of next week, because next week I would like to explain how we go from Alexia's talk to standard quantum mechanics. But just standard quantum mechanics, there is already, but so here I thought, because Carlo asked this question, what makes a context? So in next talk, I can tell a few words, but you know, I think what I will make next week is basically going to the type 1 quantum mechanics. And then you will ask me, yes, but they are contexts, why are they classical? So
Philippe,
now
let's discuss this next week. And Hippolyte
sure.
has a question.
So no, it's just that, so we already had some kind of similar discussions with Alexia about Wigner friends and stuff like this. And so we agreed on the fact that CSM was close to Carlo's interpretation, because you agree on that the fact that quantum theory is about everything, it's about everything but not anything. I don't know if you remember this quote.
Yes, sure.
It's universal, and this discussion is a little bit like confusing me, because so I still don't get if you agree that quantum theory is universal, as in Carlos' interpretation, even though sometimes when you define the context, well, you will have what I call the meta-theoretical object, but anyway, so.
Okay, before Philippe answers, I may try to squeeze an answer. There are two ways of tackling the problem, which basically corresponds to the history of what we did. The first one is that, and that's what I tried to show today, if you have a classical context and a quantized system, then you have randomness, and Philippe will show next week that it is enough to get quantum mechanics, which he calls type 1, the one that we know with Hilbert spaces and stuff. And that's why I said, if we pick up this very specific partition of the world, we already get something huge, which is type 1 quantum formalism. Then you can start digging, because there is this bothering question, but what makes a context? Because in the end of the day, we like reductionism. So we like trying to think in terms of a context being made of systems. So what would make it switch to the classical behavior? And then comes the last paper of Philippe, which talks about the difference between type 1 and type 2. And then we can see that indeed, if we try to apply type 1 algebra to the classical context, we fail. And that will be the next, the second part of Philippe's talk next week.
The conclusion.
Yes. Does it clear a little bit?
Yeah. Yes. So the discussion we had are on type 1. Okay.
Absolutely.
Okay. So with this, I agree.
All the discussion we have are on type 1, except it goes to this algebraic thing, which are really unpleasant, because the mathematics are very difficult. But I think now I'm convinced that they are needed, and that we miss something by ignoring them.
But so yeah, it's because you want to go further than just every object can be described by quantum theory, but we need some kind of classical and quantum.
This is a natural question, yes.
Take the cut.
Yeah.
You want to extract the cut.
Yeah.
Okay.
But then I'm confused, Alexia, because I'm confused about the argument, because where am I wrong? My understanding of 100 years of discussion of quantum mechanics, which have been wonderful, we've learned plenty of things, it's the following. I mean, the reason people discuss interpretation of quantum mechanics, the reason people are not happy is the way I understood it. It's the following. It's basically Schrödinger cat or Wigner friend. Namely, that's what makes people worry. So to the extent in which I can think there's a classical world and I interact with quantum systems, nobody has any problem with quantum mechanics. It's a fantastic theory. It tells me how a quantum system interacts with the classical world. It's unproblematic. You're putting it very cleanly, what it says, what it does, but nobody said there were a problem there. You can clean up. The problem that gave rise to not just relation quantum mechanics, but many worlds or Bohm interpretation of Cubism, Fuchs, Chris Fuchs and company, and all the others, has always been, but wait a minute, the classical world itself must have quantum properties. So if I get rid of that, where's the what are we discussing?
Because you put quantum formalism first here.
Well, I mean, that's a good position. I mean, you're a good teacher of quantum mechanics, but you're a good teacher of quantum mechanics with the classical world, which is something.
Well, so maybe I can tell
contextuality
what I was bothered with was I don't know why I should put Schrödinger equation first.
I never learned quantum mechanics with Schrödinger equation first. I mean, I learned quantum mechanics with apparata, interactions, Hilbert spaces first. Heisenberg did quantum mechanics 1 year before Schrödinger, as I always remind people. I mean, the idea that the way the equation comes first is a late idea that confuses everybody. We'll agree, we're all in this mind frame. With none of us go in the direction of here. I mean, I don't know the people, everybody. But those I know here, none of them is like, I don't know, Max Tegmark. There is just a huge wave function, and then from there, we extract everything else. It's between that and just textbook quantum mechanics, we're all more in the Messiah presentation, or Dirac or Landau or anybody else. But if you read Landau, for instance, it says clearly, I mean, the problem with quantum mechanics is that it assumes a classical world, which should be an approximation within quantum mechanics. So that's the problem. If you say there is a classical context period, well, so where is the problem? I mean, of course, the quantum system is contextuality. You're stressing contextuality, but you're not certainly the first one that stresses contextuality. There are plenty of schools that say the entire point about quantum mechanics contextuality.
Well, Carlo, I agree with you, but then, yes, this is the point. Either you postulate the classical world, and then you are sort of happy, and there are different ways to proceed. Our way to proceed with Alexia is CSM, but okay, in some sense, the problem is solved by postulation of a classical world. It's to postulate zero. There is a classical world, and then we start from that. Now, we do that. We are sort of happy with that. This is what we did at the beginning. But there are many, many people in this discussion like that, which tell you, which ask us, but why is your context a context? And then after that, I have started searching for appropriate mathematics. Since usual type 1 mathematics tell me my context should be a fuzzy many world, and clearly it's not that. I try to look for appropriate mathematics, which tell me that my context is a context. And what I think is now, I'm really not yet an expert on that because it's sort of difficult, I repeat it. I think algebraic quantum theory gives an appropriate framework. But there is this question of basically managing infinities. I think this is the thing we are doing very poorly, and actually it's obvious in separable Hilbert space, which is type 1 quantum mechanics, you cannot take properly infinite limits because they blow up the structure of your space. So you have to change the mathematics.
On the subject of problems with infinities.
Sorry?
On the subject, I don't know, can you hear me?
Yep.
Oh, perfect. Yes. So on the subjects of infinities in mathematics in general in relation to mathematical physics, I mean, some of the problems often seem that we have a sort of strange definition where we have no algebraic definition of an infinite thing. There's no infinite number we can go to. But I don't know if you've looked in this direction at all. But in terms of non-standard analysis and hyperreal numbers, often if you have a first order statement of what you want, you can extend it to an infinite statement. That is, you can take, your finite version that you're very happy with and say, okay, this is a first order statement. Now I can say it about infinite quantities. And you can keep everything, basically. There are subtleties if you're asking for things like subsets. But perhaps looking in this direction might be helpful for you.
Well, I did not look in. What I looked at is the most standard, what is usually called algebraic quantum field theory, which is a theory by Segal and Haag and C-star algebra, von Neumann algebra, all these things. Mathematics is really huge, and I'm not a mathematician, and I'm easily lost. So I try to find a track, but from what I've seen, I think there are mathematical answers. I think many of these problems are poorly formulated from a mathematical point of view. So what would be the good mathematics? I have some hints, but since I'm not a mathematician and not even a theoretician, I guess I have trouble finding my way in this stuff, but I see ways which, this algebraic stuff was extremely active in the 70s. It was Carlo wrote paper on that, and maybe Mauro too, and then it's sort of fading. Why is it fading? My view, by looking at many papers, is that basically it went out of the hand of physicists. It went into mathematics, pure mathematics. And there are many mathematical papers. But if you look at all these mathematical papers, you feel something interesting. But if you want to bring it back to physics, it's really tough. It's all topologies. You have, okay, I will skip details. But in my view, I think this is... this faded, I don't know. I think this fading was due to a shift from physics to mathematics. And so physicists were not able to catch the right. But maybe you know much more than me on that because you are theoreticians. I am just a poor experimentalist trying to understand this thing. What I'm convinced by is that type 1 quantum mechanics is misleading. Really, if you want to go to the macroscopic world, type 1 quantum mechanics just leads you to wrong conclusions because of inappropriate mathematics and especially inappropriate ways to take limits.
Sorry, if you have a follow-up.
Yeah, just comments on what was said there. So with regards to, I suppose this is one-sided. In advance, I work in sort of the diagrammatic quantum mechanics stuff, the ZX, ZH, for those of you that I've bothered with this before. And in that direction, I would argue that a lot of the C-star algebra stuff, being often difficult to work with, went in the direction of categorical descriptions and thereof diagrammatic descriptions more recently. So I don't think it's entirely dead. And indeed, some of my questions about in this area that I'm working on at the moment are problems with limits, basically, because you run into something similar. You start thinking, okay, well, what if my stuff's infinite? What if I have an infinite number, or it can be partitioned infinitely? And suddenly I start asking for what turns out to be an algebraic infinity is what I'm looking for. And I wonder if there's a similar relationship to what you're saying. However, with the type 1 quantum mechanics, to go back on something that Mara said earlier, that many students probably don't have a clue what that is versus type 3. I am one of those students, forgive me. And I would consider myself reasonably mathematical at this point. So I wanted to try and understand what you meant by wrongness. And to really articulate that question, I suppose I would say, okay, so you have physics underlying, you have the quantum physics that you want to work with, that is in you have physical things that physically happen. And then you say, okay, well, I have von Neumann, for example, structural quantum mechanics. You say, well, this is my language for describing this physical stuff I see. And so for something to be wrong, as far as I'm phrasing wrongness at least, then there are two things. I want soundness and completeness of my language. I want to know that every underlying truth that I say in my language is actually true. It happens in the physical world. And I also want to know that all the truths that physically go on, all the things that, all the equations I make, all the equalities, are also true in my language. What physical things happen that one would reasonably say is in the framework of quantum mechanics, not going off to limits where relativistic effects take place or gravity, so on and so forth. What things happen physically but fail to be represented in the language? What situations are you referring to?
Well, type 1 quantum mechanics is all unitary, so you just go to many worlds, and so the obvious existence of a single macroscopic world does not fit in.
But you don't need to go to many worlds because you can take relational quantum mechanics and it's also type 1 and it's working, right?
Well, okay, probably we will not end up the problem.
Yeah,
I just gave a few arguments. Yes, I was stimulated by Carlos' question about what makes a context. So I just told you what I think about it now. It's not a final answer anyway.
So, sorry if I jump. So we're running out of time. I guess there are probably a lot of other discussion, myself included. So if you agree, maybe next time, if there are a good number of questions about the first part, because I might be wrong, but I'm afraid that if we move to the second part, we do not discuss enough some of the stuff of the first part that I think are worth discussing. So if the speakers agree, the next time I would probably start at least 20-25 minutes with a question, mostly from people that didn't have time today, and I'm sorry about that, from people that didn't ask questions on the first part, and then we move on to the second one, if you all agree.
Okay, fine.
Any way of doing this a bit later?
Oh yeah,
Yes.
sure. I mean, this time we didn't have time to go back and forth in the email and change, but definitely. And
yeah,
thank you.
Thank you again for waking up so early.
Thank you very much.
No, but that was extremely interesting for me, so I just didn't want to miss it.
So yeah, we will try probably to do 1 to 3, so that makes it 3 hours later.
Yeah, perfect.
Yeah.
Okay,
that's fine.
Well, thank you, everyone, and
thank you very much.
So which time did you tell?
Yeah, sorry. We will try either 1 or 2 p.m. But I'm gonna send you a doodle or something of this type of, and so democracy will lead. We will see. And anyway, we will record the meeting. So if someone really can't join, of course the speaker have to, but for everyone else, we will record the meeting. Okay.
Thank you.
Thank you.
Bye.
Thanks, Philippe.
Thanks for the talk. Thanks, Alexia.
Thank you, Christian. Thank you, everybody. Bye.
Ciao, ciao.